Hello, welcome to all. Today also we are going to continue the electric field and electric potential. Okay, yeah, the outline of today's lecture is the potential at inside points of uniformly charged sphere. In the previous lecture, we calculated the potential at the outside points of a uniformly charged sphere. Okay, today we will calculate the potential at the inside points of a uniformly charged sphere. After that, we will go for the potential of the spherical shell. We will find the potential both at inside and outside points of the spherical shell also. Next, we will go for the spherical shell within which a point charge is located. In that case also, we will find the potential at the inside and the outside points. Okay. Finally, we will study about an interesting example of electrostatics Faraday's cage. Okay, with this our electrostatics will be completed. Okay, right. Okay. Today we will start with the uniformly charged sphere. Yeah, in yesterday's class we are already calculated the potential at the outside points of the uniformly charged sphere. So in this lecture, we start with the calculating the potential at the inside points of the uniformly charged sphere. So case B, potential at the inside points. Okay, let us call this as phi. So in. Okay. Now, yeah, you see in the slide here. In this case, this is a symmetrical object. That's why, in order to find the potential of such objects, first of all, we are taking the electric field, which is calculated from the Gauss law of electrostatics. So we are making use of those results for inside and outside the sphere in order to calculate the potential at inside points and at outside points respectively. So, in this case, let us take the field inside of the uniformly charged sphere in order to evaluate the potential. Okay, what is that? E inside the sphere is, what is that? You see on the slide, this is QR by 4 pi epsilon naught R cube. Here R is the radius of the sphere, charged sphere. Okay. Now, you see, this is the charged sphere. Okay. Now, this is the origin. This is the radius of the sphere. You want to find the electric potential at some inside point. Say this point is P, which is located at R. Okay. Now your R is less than. This is R is less than R is. Okay. Now, what formula we have to use here? The relation between potential and field. Okay, I will write the general formula here. E is equal to here phi. Need phi. Phi is equal to minus of integral E dr. Okay, otherwise E dot dr. But in this case, angle between the field and this R is a 0 because R is a direction. R is directed in this way, field is also directed in this way. So you have simply EDR. Okay. Now you want to find the potential at the inside points now. So you write here foot in, foot in, foot in. So E in is here, you have to make use of this. Okay, that means this is equal to minus of integral q r by 4 pi epsilon naught. Okay, 4 pi epsilon naught. Yeah, r cube dr. Now here we want the potential at P. Generally, we define the potential with respect to a point at the infinity. So we start from infinity, we bring the unit positive charge from infinity to this point under consideration. Point under consideration. So if you want to know the potential at some point inside of that, here you have to include the work done to bring the charge from infinity to up to the surface. Okay. So here this is a term applicable to where R to R. R to R, or say capital R to small r. Okay. But another term, what we have to include here, plus minus of, that means minus integral. Okay. What is this? This is infinity to, okay. This is, okay, this is, okay, R to R now. Now, which term you have to include from infinity to R? Okay, infinity to R. So, infinity to R. Okay, yeah, but here, infinity to R means this refers up to the surface of the sphere. Okay, so outside, how much field is there? For outside points, you have to write E out here. See, E out, what is that? You see in the slide, that is Q by 4 pi epsilon naught R square. Okay, simply is a Coulomb's law. Okay, dr. Because for the outside points, what will be the field? According to Gauss law, Q by 4 pi epsilon naught R square. See, plus charge is filled inside this sphere. Okay. And now this will, the addition, the sum of these two terms will give you the potential at the point P. Okay, this you have to note. Okay, right. So now I will write here. What are the two terms you have to calculate? I will write here again. Psi in means at the point, okay, P is equal to, yeah, now what is your first term? Minus R to R QR by 4 pi epsilon naught R cube dr minus infinity to R. This is q by 4 pi epsilon naught. Yeah, what is this? R square dr. Okay. Now, let us calculate the first term. What are the constants here? Q by 4 pi epsilon naught R cube. These are all the constants. Inside the integral, we are only left with R dr. Here also, you may take 4 pi epsilon naught outside. My infinity to R integral. Next, inside the integral symbol, you are left with 1 by R square. Okay, now this is q by 4 pi epsilon naught r cube. What is this? What is the integration of r? This is r square by 2 with limits capital R to small r minus q by 4 pi epsilon naught. This is, what is the integration of 1 by r square? This is minus 1 by r infinity to r. Okay. Now this is equal to minus q by 4 pi epsilon naught r cube. Okay. After substituting small r, you have r square by 2. After substituting capital R, you have capital R square by 2. Okay, this is over. Next, q by 4 pi epsilon naught minus 1 by r, minus of minus plus 1 by infinity. Okay, now this is equal to here q by 4 pi epsilon naught r cube. You take minus inside. Okay, then you have 2 r square minus r square by 2. Here this is 0 minus q by 4 pi epsilon naught. You take minus outside, this is plus 1 by r plus 0. So now you have here finally phi in is equal to, this is q by 4 to the 8 pi epsilon naught r cube. Okay, r square minus r square. What about this? Plus, okay, q by 4 pi epsilon naught into 1 by r, q by 4 pi epsilon naught r. Okay, so now here what is the denominator? Here you are having q by 4 pi epsilon naught r. Okay, now you take common, you take otherwise here you have 8 pi epsilon naught r cube. Here you have 4, that's why you multiply with 2. Okay, here you have r, here you are having r cube. So you multiply with r square, both numerator and denominator. Next you have q by 8 pi epsilon naught r cube, r square minus r square plus 2q r square by 4 to the 8 pi epsilon naught r cube. Okay, now you have the same denominators. Now you can take the LCM. This is equal to, what is your LCM or common factor now? Q by 8 pi epsilon naught r cube is now common. Inside the brackets you have r square minus r square plus 2 r square. Why? Because q by 8 pi epsilon naught r cube is common. Right. Now q by 8 pi epsilon naught r cube, inside the brackets you have 2r square plus r square. That means 3r square minus r square. Okay, this is a final expression for the potential inside the uniformly charged sphere. Therefore, psi in or psi p is equal to q by 8 pi epsilon naught r cube 3r square minus r square. This is the expression giving the potential inside of that uniformly charged sphere. We already calculated the potential on the surface of the uniformly charged sphere. Here, whenever you make small r is equal to capital R, then you reach the surface. Then this has to give the potential on the surface. If this answer and the previous answer correct, this expression is correct. Okay, now I will write here. Yeah, at small r is equal to capital R, psi in becomes phi surface. Phi surface. Therefore, phi surface is equal to, now this is phi surface whenever you put r is equal to capital R. Okay, 2 by 8 pi epsilon naught r cube 3 r square. You have to put small r is equal to capital R minus r square. Now what happens to this? This is 2r square. So q into 2r square by 8 pi epsilon naught r cube. Okay. Now what is the final expression for the potential on the surface of the uniformly charged sphere? Therefore, phi surface is equal to 2 1 ja 2 4 ja. This is equal to q by 4 pi epsilon naught. This is r square, this is r. Okay, r square cancel, you are only left with one r here. Okay, so what is your expression for the potential on the surface? Q by 4 pi epsilon naught r. This is exactly coinciding with the previous expression derived using the potential at outside points of the uniformly charged sphere. Okay, why? Because it is an interface. It comes, you may get the expression for the surface both by using the solution for outside points as well as inside points, but the expression should be the same. Okay, right. Yeah. See, next, what is the difference between the formula, this formula and this formula? Okay, what is the meaning of the formula for of the potential for inside points? Okay, whether it increases or decreases. See, what is the total formula? Here we look, we got for inside points, psi in is equal to q by 8 pi epsilon naught r cube 3r square minus small r square. Okay, this is the expression giving the potential for inside points of the uniformly charged sphere. What's the meaning of this? What happens when you change the r? When you change r, that means as you increase the small r, what happens? The psi in value uh, decreases. Psi in value decreases. Because you have to deduct something from this expression. Okay. So, whenever you increase small r means whenever you move towards the surface, what happens to this potential? This potential value decreases. So, from the center to surface, what happens here? Potential decreases. Potential decreases. That means at the surface you have this much potential. Let us see what potential you have at the center. That should be the maximum one. Okay, at r is equal to 0, this psi becomes psi center. Okay, this is equal to at r is equal to 0, you reach the center, potential in the center is now q into 3r square minus 0 by 8 pi epsilon naught r cube. Okay, let us write here. Yeah. So what is otherwise you write not or C, you may write also center C. So psi C center phi C is equal to, this is minus 0 means you have to retain only first term. Then what happens? 3q here, 1 r square, to r square is here r square is cancelled, you are left with 1 r. So what is your expression? 3 q by 8 pi epsilon naught r. See, what is the difference between this relation and this relation? You may express this in terms of this expression, surface potential. Then what happens? You just simply write 3 by 2 q by 4 pi epsilon naught r. What is this q by 4 pi epsilon naught r? It is the potential at the surface. So, potential at the center is equal to 3 by 2 times of the potential at the surface. Surface. Which one is higher? 3.3 by 2 means 1.5. So, potential at the center is 1.5 times, 1.5 times the potential at the surface. So, you have large potential at the center. As you move away to the surface, okay, as you move away to the surface, the potential goes on decreasing up to the value q by 4 pi epsilon naught r. Decreasing is there here to here. This is decreasing sign. This direction is a decreasing phi direction. What happens? You increase r after crossing the border. Which formula you got? Usual Coulomb's law formula you got for that, na? See, it falls by 1 by r. Okay. It falls inversely as r. That means, okay, here the fall will be like this, okay? Outside points. So, for both at the outside points and inside points, we gradually observe the decrease in potential in case of uniformly charged sphere. Sphere. Okay. It's not the field. It is not the field. Okay, as you increase R inside the uniformly charged sphere, what happens to electric field? It increases. Potential field. This electric field increases. Why? Because you have E is proportional to small r there. Okay, right. Okay. What happens to the field outside the uniformly charged sphere? Okay, it varies as Coulomb's law. That means E varies inversely proportional to r square. But here you have phi inversely proportional to r variation. There you have E inversely proportional to r square variation. Okay, there is a difference between the electric field and potential of the same object for both interior and exterior parts. Okay, that you have to note. Yeah, you can see the results here on the slide. Yeah, you see here the results. You can see the results here. Okay, phi at the outside points is q by 4 pi epsilon naught r. Phi at the inside points is here you may see that on the slide which we derived just now. Okay, q by 4 pi epsilon naught r cube into 3r square minus r square, which you can see on this slide. Okay. Now let us go for some another object which is very similar to this one in the geometry, but you do not find any matter inside of that sphere. That is hollow sphere or spherical shell. Spherical shell. Let us try to find. Let us try to find the potential inside and outside of the spherical shell. Why? Because we are already know the electric field inside and outside of the spherical shell. By using the Gauss law, we did it. Okay. Now let us just take out the results for electric field and try to evaluate the potentials for that object. Yeah, now I am moving for this object. Okay. So electric field of the spherical shell. You know what is the electric field for outside points of the spherical shell? Okay. Okay. Next problem is spherical shell. Okay. First, let us take the fields and then let us try to evaluate the potentials. See, first of all, you see here, in case of this spherical shell, you have field for inside points as what is the field inside for inside points? 0. For outside points, you have the field as Coulomb's law, Q by 4 pi epsilon naught r square. Okay, let us first try to find out the potential for the outside points. Okay, this is the spherical shell. Okay, whatever the charge you have on this surface or on this area. Okay, very thin spherical shell. Okay, one is charge is only on this surface. Okay. Now, what are the formulas for the electric field? A for inside points. Suppose that you have, okay, first of all, let us take outside points. Okay. You are choosing some points outside of this, say this is your OP. See, what is the electric field here? A for outside points. For outside points. See, for outside points, what is your E? E is nothing but it is nothing but the Coulomb's law. Q by how much charge is there? Total plus Q. Q by 4 pi epsilon naught r square. Okay. By using this, we calculated by using the Gauss law of electrostatics. Now I am using this expression in order to evaluate the potential for outside points. Okay, which relation we have to use here? Same relation using the relation phi is equal to minus of integral EdR. It is also symmetrical object. You just simply have EdR. Now we have to put this E. Okay, for outside points there is no problem. Your integral is only a single integral. You need not to split the integral. Okay, here what are the limits for this? Phi out simply infinity to some point outside the spherical shell, which is located at the distance small r. Small r. Okay. Now you just substitute this E here. Okay. I will write here. Okay. Phi out is equal to minus of infinity to r. Yeah, what is E? Q by 4 pi epsilon naught r square dr. Okay. This is equal to minus What are the constants? You just write the constants outside. Q by 4 pi epsilon naught is a constant. Okay. Inside the integral symbol, just you have to write 1 by r square dr. Okay. What is the integration of 1 by r square? Minus 1 by r. Minus 1 by r limits infinity to small r. Okay. Now, to substitute the limits, minus q by 4 pi epsilon naught. Yeah. First upper limit, there is no change, minus of minus plus 1 by infinity. So second term will be 0. So what is your final answer? Q by minus into minus plus 4 by 4 pi epsilon naught r. Okay. Therefore, what is the expression for the potential at outside points? Q by 4 pi epsilon naught. It is also a simple Coulomb's law. Okay, Coulomb's law relation. We can get this by using the Coulomb's law. Okay, F or E. Okay, right. Phi out is equal to Q by 4 pi epsilon naught R. This is the general formula for the potential. Okay, for the object with charge Q. So for outside points, you do not have any difference for uniformly charged sphere or spherical shell. Okay, entire charge is within the limits of that sphere. Okay, that may be spread out uniformly, or that is only residing on the surface of the shell. It doesn't matter. You finally have the same expression. Okay. Now, what is the difference between the potential of a uniformly charged sphere and a spherical shell? Yeah. In this next case, that means in case of potential at the inside points, you see the different formulas in these two cases. Okay. Now let us go for the next case. Before that, you see how the potential is varying for the outside points. As you increase r, that means as you move away from the center of the sphere, potential gradually decreases as r. That means phi is inversely proportional to here, phi out is inversely proportional to r. E out is inversely proportional to r square. Okay, you know that. Right. Yeah, next let us go for the inside point. Now let us consider the inside points. Okay. Yeah. Now we are considering a point here, which is also at the distance small r. Yeah. Right. B for inside points. So what is field for inside points? Yeah. Whenever you are going for the inside points, in case of potential, you are required both the fields at outside and inside points, as I already told to you in the case of uniformly charged sphere. Okay. Now, E out 2 by 4 pi epsilon naught r square. Okay. E in how much field is there where there is no matter, no field. In case of spherical shell, this is 0. Okay. Yeah, you see on the slide. Now we want to find the potential at the inside points. Phi inside a point located at the distance r from the center. Okay. Now, which relation you have to use here? Using same relation. Phi is equal to minus integral EdR. Minus integral EdR. So now, let us apply this formula here. Phi in is equal to, here you need potential. You have to bring the unit positive charge from infinity to that point. because situation is different up to the border and after crossing the border. Field is different. That's why you cannot bring the charge directly from infinity to the inside point. First, you have to bring the charge up to the surface. Field is different there. So let us write separate integrals for outside for outside region and inside region. So you are bringing the charge from infinity to r up to the border. Okay, up to the border. This is E dr. This is E out minus na here. Okay, again minus. Now you are entering into the shell. So in the inside part, how much field you have? 0 dr. But what are the limits for the inside points? What are the limits for the inside points? Here, for the outside points, here, what we have to write here? Infinity to up to the border means r is equal to capital R. This is okay, right. Minus here, R2 for inside, whenever you are bringing the charge from out infinity to inside, from surface to up to small r. Okay, capital R2 up to here, this is capital R, up to this point, this is R. So your limits of integration are capital R2, small r here, capital R2, small r. Okay, I will write here now. So in this way, whenever you want to calculate the potential at the inside points, you have to take into consideration the electric fields both at the outside points as well as inside points. Without that, you cannot get the correct expression for the potential. You have to remember this. This is very, very important. Right? Now, phi in is equal to, what is E out? Let us write it now. Here, minus integral infinity to r. Infinity to r. What is E out? Q by 4 pi epsilon naught. Outside points E r square dr. Anyway, the second term is 0. Minus 0. Why? Because E is 0. Right. So, for inside points, you have how much of potential? Minus, take 4 pi epsilon naught outside, integral infinity to r, integral infinity to r. So what is phi in now? Minus, take 2 by 4 pi epsilon naught outside, limits of integration are infinity to r, 1 by r square dr. This is equal to, now what is the integral of 1 by r square? Q by 4 pi epsilon naught. This is 1 by r, infinity to up to r. Okay. So now you have phi in is equal to minus q by 4 pi epsilon naught. Now apply the limits of integration, minus 1 by r, minus into minus plus 1 by infinity. So you have, this is 0, second term, first term is minus 1 by r, minus into minus plus q by 4 pi epsilon naught r. Now this is a final expression for the potential inside the spherical shell. Is it varying with the small r? It is independent of small r. So whatever the potential you have on the surface of the spherical shell, you have the same potential all throughout the inside portion of the spherical shell. Throughout the region inside, you have the same constant potential, that is q by 4 pi epsilon naught. Up to the surface, you will find the same potential. But this does not happen in case of uniformly charged sphere. Okay, as you move from the center to surface, what happens? Electric potential decreases. Electric potential decreases there. But here the potential will not vary at all. Potential will not change at all. That potential will be the same as that on the surface of the shell. Okay, this is what the difference between the spherical shell and uniformly charged sphere. Okay, right. Now, yeah, you see here, if you plot the graph between the R and the potential, so what will be the shape of this graph? For inside points. That means up to the point, this is a shell. Okay, here up to the point, your E is up to the radius, your phi value, we are phi, not this one. Your phi is constant in between R is equal to R is equal to minus R. Okay, up to the radius. So along the diameter you have the same potential. As you move out of the sphere, what happens? This varies as 1 by R. This varies as 1 by R. So up to R is equal to R and R is equal to minus R, you have zero field. Zero field. Okay? Zero. You have how much field outside of this spherical shell? See, E is equal to Q by 4 pi epsilon naught R square. So it varies as 1 by R square. It varies after going to this point. You have some such relation. Okay, such a variance of E. Okay, for outside points. Right. This is a border. This is the border. So where do you have the maximum value for E? At the surface. At the surface. Okay. Maximum value for E at the surface. As you move away from the surface, it falls as R square. Okay. Right. What about in case of uniformly charged sphere? This is for spherical shell. Spherical shell. If you take the uniformly charged sphere, what happens to this? Here, this is a potential axis. This is the R axis. Yeah. Which expressions you got for the uniformly charged sphere for the potentials? Yeah. Here this is the R axis, this is the phi axis. See, in the previous case, otherwise you take the field versus distance graph. What happened up to the center? E value is increasing as R. E value is increasing as R. On both sides up to the R is equal to R, up to R is equal to R minus R, this one. Okay. See, when you move away from the surface of the uniformly charged sphere, what happens? It goes as ordinary Coulomb's law. Okay. Then you get the relation like this. This is proportional to R. Okay, this is inversely proportional to r square, r square. Okay, this is for the uniformly charged sphere. Okay, this is for the spherical shell. Spherical shell. Okay, this is also here 1 by r square. 1 by r square. Right. Next, in case of potential versus r graph, what happens for the outside points? Yeah, your potential varies as or outside of the uniformly charged sphere, but inside points you have the potential variance as some constant minus r square, some constant minus r square. Okay, this is about the electric potential and electric field of uniformly charged sphere and the spherical shell. Okay, now let us go for our next other topic. Yeah, this is a yeah spherical shell, spherical shell with a point charge. Yeah, here we take a spherical shell. Okay, it is having the radii A and B. Suppose that I am placing a charge plus 2 here. Okay, then what happens to it is located at some distance small r. Okay, plus 2 is here. This distance is uh, small r. This is the center. Okay, in this case, what will be our potential at the outside points? What will be our potential at the inside points? Basically, let us try to find the potential at the center. It will be very easy to find. Here, here we have to know the properties of the conductor. Okay, whenever you put the charge, whenever you bring the charge very near to the conductor, what happens there? See here, this is uncharged conductor. I am placing a plus Q charge here. This induces charges on the inner and outer surfaces of the shell. Okay. Due to this charge, here you find some minus charge. Here you find some plus charge. Okay. This charge will be minus Q. This charge will be plus Q. Okay. Now what happens is here the total charge for this portion will be gets cancelled. So whatever the charge inside that is there, that appears for the outside points. So what will be the potential? Phi out. Phi out is equal to simply this is Q by 4 pi epsilon naught. Q by 4 pi epsilon naught. Say this charge, the distance between now for the outside points, this is small r. Here to here, let us call this as a small r. Now for outside points, we are reading the first case outside points. So these outside points C, the total charge Q located at the center O. So what is the distance between this point and O? Let us call this as R Q by 4 pi epsilon naught R. Okay. So the potential at one outside point P, which is located at the distance of small r, is now given by psi out. Phi out is equal to 2 by 4 pi epsilon naught R. Right? Next, let us go for the inside points, particularly at O. Okay, inside points. Next, let us consider inside points. Phi in is equal to how much? Particularly, let us take the case of the point being located at O. See how many charges are there now? This is plus Q charge, this is minus Q charge, this is plus Q charge. So now here we have to use the superposition principle. Superposition principle. Phi in is equal to, first phi 1 plus phi 2 plus phi 3. Three charges are there. Two are the induced charges, one is the original charge. Okay. Okay, for the original charge, where it is located from here to here, R. That's why what is the formula for potential? Charge is anyway Q 4 pi epsilon naught R. Why? Because it is located at the distance R from here. Next, what about this minus charge? So this is minus Q. Okay, where it is located? It is located inner radius. At inner radius, na? 4 pi epsilon naught A. What about this third charge? It is located at the outer radius plus Q by 4 pi epsilon naught B. So what will be your total answer? Q by 4 pi epsilon naught. Okay, 1 by R minus 1 by A plus 1 by B. Phi in. Okay. This is the potential at the center of the spherical shell with a charge inside of it. The charge inside of it. Okay. Here, when you increase the radius of the inner shell, what happens? If you increase this value decreases, its value increases. Okay. If you decrease this, what happens? Its value increases, so its value decreases. So whenever you decrease this phi in value, what happens to phi in value? Decreases. Okay. Whenever you increase A, phi in value increases. Right. Yeah, this is about the potential of a spherical shell with a point charge. Okay. Right. Next, let us stop this lesson with the last slide. Yeah, a very interesting topic we want to discuss now is Faraday's cage. This was discovered by the Michael Faraday in the year 1836. Okay. Yeah, it is one among his innumerable inventions. Okay. What happens here is a Faraday's cage is nothing but a conductor with a cavity, or it is a wire mesh box. It is a box made with wire mesh. See, by using this, what happens? What is the importance of this Faraday's cage? See, you may take any enclosure, including a car, something like that, as a or a lift made up of lift chamber, metal can be taken as a Faraday's cage. Faraday's cage. See, what happens in Faraday's cage? It can be used in MRIs. Okay, MRI room will be made as Faraday cage in order to get the uninterrupted signals correct reading. So to protect the electronic equipment from external influences, we use this Faraday's cage. We put our instruments inside of this Faraday's cage. Then fields outside or the charges outside the Faraday's cage will not affect the instrument. Okay. Okay. How this is possible? See, this is a Faraday's cage. Okay. You are applying some external field. Some external field is there. Your instrument is here. Okay. Whenever you apply the field. Here you have less Q. Okay. Okay, field lines are coming like this, means on this side you have plus Q of the field, on this side you have minus Q of the field, minus charge is here. This is about this charge is the origin of this electric field. Okay, external charges are there. See, the field is like this. Now what happens here on this side, you have positive charge, so negative charge is induced here. Negative charge is induced here. So on this side, if it is a minus charge is there, what happens here? Positive charge is induced here. So since this charge and this charge nullify each other, you don't have any effect of the field. Suppose that external field is Ex. Due to these charges, you have some internal field or E induced, which is equal to minus of E external. So E total is equal to E external minus E external is equal to 0. So total field inside is again 0 as before. So you do not have any effect on the electronic apparatus inside of this. Okay. So any object can be protected by the high fields by using this Faraday's cage. Very simple instrument. Simple instrument. Okay. See here polarities are changing. This is plus, this is minus for original charges or original field. See here on this side you have negative, on this side you have positive in case of induced charges. So induced field is equal in magnitude to the external field, but it is having reverse direction. So the net field in this region will be 0. So in this way, you can protect the electronic equipment by using the Faraday's cage. Okay, this can be used in MRIs, this can be used in the cables. Okay, this can be used in the operations of high voltage region. This can be used to protect, to stop the signals, to stop the incoming phones, incoming signals and outgoing signals. Okay, these things can be used at several places. So Faraday's cage is a very important application in electrostatics. This was for the first time discovered by Michael Faraday. Here, what happens in the conductor? Whenever it is exposed to a charger field, that is important here. Okay. Here, induced field. This here, due to the external field, we have induced field. That is important. Due to induced charges, That is what the principle of Faraday's cage. Okay. Let us stop with this. Thank you.